Welcome back, physics fans, and here we are on the last part of the last lesson on power and efficiency. So let's learn about power. It's a very common word that's used for electricity and stuff like that, because you cut the power. It's very powerful. How powerful is your engine? We need to understand what is power. And we start off right away with the definition of power. Okay, and that is power is the rate at which work is done or the rate at which energy is transferred. And that's our definition. Now think of it in terms of how much work is done per unit time. Power is measured in watts. That's the unit for it, watts. And we understand that 1 watt is a joule per second. So we have our units over here is a watt is a joule per second. But the problem with writing watts as a W, we also have W as work. So Mr. Curl always writes out watt, not abbreviate the unit as a W, just so we don't fall into a trap. Do you have to? No. But I don't want people to go 1 times the work here. And work or change in energy is measured in joule. Time is measured in seconds. There are other units of power out there, like horsepower. And if you Google it, you get like 1 horsepower is equivalent to about 745.7 watts. And in Physics 11, we'll just use right now that 1 horsepower is 746 watts. I won't tell you to memorize that. I'll have that on your quizzes. So the formula for power is P equals W over T. Now, we have lots of different versions of that now because this is the end of our lesson. We could have that power is the change in energy over time because work is the change in energy. We also have that it could just be something that is being lifted up. So the only energy change is the change in potential energy, and it's not speeding up. You could have that. You could also have that the power is the change in kinetic energy over time. Then you can rearrange that, right? So you could get that the change in kinetic energy is equal to the power times the time. That's that same formula. So there's a lot of different ways to manipulate it, but this is the formula. Power is work over time. Okay. There's a little play with a formula here that we'll talk about much later. And then there's a talk about efficiency here. But we're going to be doing those in a second. The first question is question 0. What is a kilowatt hour? What is a kilowatt hour? Well, why am I asking you that? Well, let's just take a look at BC Hydro. They're supplying our electricity into our house. What are they selling us? Are they selling us power or are they selling us energy? Because these are different things now. Power is how fast we use the energy. So what are they? Are they selling power or energy? Well, we take a look at a BC Hydro bill, and this is a sample one, and they say that they have different rates to sell you the power, and the first rate is for the first 1,332 kWh. They sell it to you for about 8 cents per kilowatt hour. And then after that, then they raise the price. So the next 268 that this person used was at 12 cents. So they raise the price as you use more and more. Okay, that's what they sell it to you. But they're selling it, whatever they're selling you, the electricity, in kW.h, kilowatt hour. Kilowatt times hour. Well, a kilowatt is 1,000 watts. And an hour is 3,600 seconds. So now we're in our base units of watts and seconds. This is going to be 3,600,000 watt seconds. What is a watt second? Go back to here, go back up. What is a watt second? Looking at units, if I bring the second up there, then I get a watt second, and that's going to equal a joule. So 1 watt second is a joule. So this is equal to 3,600,000 joules. The takeaway here first is they're selling us energy. They're selling us joules. They're just measuring it in a different unit. They're measuring it in units of watt seconds. And 1 watt second is equal, well, 1 watt second is 1 joule. 3,600,000 watt seconds is 1 kilowatt hour. They're selling us in kilowatt hours, and 1 kilowatt hour is 3,600,000 joules. Okay, so the question is, what is a kilowatt hour? And that is 3.6 megajoules, or 3,600,000 joules. And that's our conversion rate. If we're asked for anything in kilowatt hours, we have to divide it by 3,600,000 if we have it in joules. So let's just do our first question here. How much work can a 5 horsepower motor do in 10 minutes? So, power is work over time. So they're asking for how much work. So work is equal to power times time. So we have power, but it's in a different unit. We want it in watts. So power is 5 horsepower. But we have to multiply that by 746 watts for 1 horsepower. That's a conversion. And then when we multiply that out, we get 5 times 746. The power is 3,730 watts. And the time of 10 minutes is 600 seconds. So the power here is, let's change it to red here as our answer. The power is because we have to multiply these together. 3730 watts times 600 seconds. And Mr. Calculator times that by 600. And we get 2,238,000. 2,238,000 joules, and that equals 2.238 megajoules. Okay. Now there's just one little tidbit of information in this that I want to talk about. Not with question 1, but that's the answer for question 1. We've done question 0 and question 1. I want to talk about efficiency. Okay? And efficiency can be calculated by the formula that I have there. Let's just quickly try a challenging question with efficiency and learn how to do efficiency here. A certain motor uses this much energy. So it uses this much energy. So it's taking in this much energy. This is the input. It's taking in that much input, and now it's raising a 30 kilogram mass to a height of 2.4 meters above the ground where it started. So we have to find out how much energy it used. So we have to use this to find out how much it used. So how much potential energy did it gain during this lift? The potential energy is equal to mgh, and it's 30 kilograms times 9.8 times 2.4. Just understand here, so we take 30 times 9.8 times 2.4. That's 705.6 joules. 705.6 joules. So the amount of work done was this. That was the output. That's how much it did. But it took in 1,300 joules to do that. Because where does this energy go? It heats it up, it makes sound. It doesn't use all of it in what we want it to do. So it's not 100% efficient. Because it takes some of that energy to do other things than what we want it to do. So we take a look at efficiency as the output, 705.6, all over the input of 1,300. So I divide this by 1,300, and we get 54.3%. Because the calculator says 0.5427. So we convert it to an efficiency percentage, and that's how efficient it is. It took 54% of the energy to lifting it, and the rest of the energy went to friction and heat and all that other type. So that's how you do efficiency. You could do efficiency with work out or over work in, or the output for the power over the power in. And the efficiency is always going to be less than 100%. Remember, smash the like button, subscribe, follow my channel. Thank you very much. Bye-bye now.